Okay. We have seen decimation interpolation. Often when you decimate a signal, you pass it through a low pass filter. Okay. Low pass filter, if it is pi, if it is minus pi, it is omega c, say minus omega c, ideal low pass filter. You make sure that omega c is sufficiently less, okay, so that after you do down conversion, that decimate by m, no aliasing takes place, because signal should be perfectly band limited. Okay. If you want to decimate by m, then omega c, this half sampling frequency, it should be less than m times, okay, because it will be expanded m times. So, anyway, you pass it through a low pass filter, so that it is band limited. Okay. If whenever you are doing, say, I am telling you, you are doing decimation. Before doing decimation, that is, you are bringing down the sampling rate, you must make sure that signal is properly band limited. That is, if it is pi and you are decimating by a factor m, then omega c should be less than equal to pi by m. Because after decimation, this can go maximum up to pi, this can go maximum up to minus pi. Still, there will be no overlap from the right hand side, left hand side, if you band limit the signal by a low pass filter, hard low pass filter with cutoff frequency omega c. Because then suppose this original signal x e to the power j omega, it is now band limited, suppose it is like this, from omega c to minus omega c, and this is pi, this is minus pi. This if you decimate, you call it x n, if you decimate it, output DTFT, we all know the formula, and there you see this omega c will be expanded, it will go to, I mean, if it is exactly equal to pi by m, it will go to pi, otherwise it will go up to pi, I mean, it will not touch up to pi, maybe go near pi, minus pi. Then on the right hand side also you will have something like this, okay, but there will be no aliasing, all right, there will be no aliasing, all right, because after down conversion, the new sampling rate and the new half sampling rate will map to pi, okay, but that will be m times small. So, omega c, now it is m times less than pi, okay, so it will not cross pi, okay, with this we have covered. So, this low pass filter is used actually, always a low pass filter is used before any down conversion, so that it is limited within a band. As I told you, cutoff frequency should be omega c should be less than equal to pi by m. This we have seen. If omega c is less than equal to pi by m, I am repeating, input band will be only within this, omega c say less than equal to pi by m. After decimation, the new sampling rate will be m times less than the original, new half sampling rate will be m times less than the original, but new half sampling rate will map to pi, okay. And therefore, signal this omega c, all frequencies will be expanded. So, it will go here, but it can go maximum up to pi, because omega c is less than equal to pi by m, all right. You remember, I mean, that formula, decimation, after decimation DTFT formula, these factors come e to the power j omega by m, okay. As a result, this expands. This thing actually was done in the class, that is why I am not going deep into it, I am just dropping a few hints. What happens? It expands by a factor capital M, but if it is, will it cross pi? Answer is no, because it was originally less than equal to pi by m. Now, new half sampling frequency is m times less, okay. So, that will map to pi, and this will expand by m times, but it will still not cross pi because of this relation, which means this will be like this within this band, and here again then. So, no aliasing, okay. Because of this we have to have a low pass filter always before this down conversion. Now, I will talk of using this noble identities which was done in the previous class. I will talk of efficient decimator, efficient interpolator. There is an Hz of filter is given. Now, look at the structure. Here the input clock rate is higher, the filter is working at higher rate, then I am bringing down the sampling rate. So, this side is operating at a higher sampling rate, this side at a lower sampling rate. That means, this side is costly, the filter is working at a faster clock, anything that is higher speed, anything that uses faster clock, that will be costly. Okay. How to make it less costly? How to make it operate at a lesser clock? For that, I remember this polyphase decomposition of Hz. Since it is capital M, I will look for a factor of m polyphase decomposition of Hz. That will be H0 z to the power m I hope you remember this very quickly. What are those polyphase factors? Suppose instead of H, I have got a sequence X. So, this is the sequence, you take X0, then mth, 2mth. So, from this X0, Xm, X2m. So, this is the 0th sample, first sample, second sample, minus 1th sample, like this, X minus m. You call this sequence P0m. Then take the first sample, okay. This arrow means 0, origin. So, now X1 is at the origin. You take first sample, m plus 1th sample, 2m plus 1th sample, minus m plus 1th sample. Okay. Place them side by side. So, 0th sample is X1, first sample is Xm plus 1 dot dot dot. You call it P1n. In general, PLN is you take the Lth sample XL, then you take L plus m, L plus 2m, like that, XL at the 0th position origin, XL plus m, L plus 2m, XL minus m, like that. And therefore, you can go up to P0, P1, PL up to Pm minus 1n. Pm minus 1n means take X m minus 1, then 2m minus 1, 3m minus 1, like that. Okay. You can have only this. If you go for Pmn, you will get back P0n. Okay, we do not need that. P0n, we just have a shift. Now, and from this you remember, we could get back the original sequence. How? You first expand P0n by expand. So, between these two m minus 1 zeros, between these two m minus 1 zeros, between these two m minus 1 zeros, like that. Then P1n also you expand between these two m minus 1 0, m minus 1 0, m minus 1 0. Then there is this. Then this sequence size shift delay by 1 at the faster clock. So, this will come below this will come here, this will come here, x1 will go there, like that. If you add the 2 now, x0 and this 0 will come here, sorry, this 0 will come here, this 0 will come here, this will come here. So, x0 plus 0, x0, x1 plus 0, x1, this plus 0, this, and like that. So, you will get something like this, x minus m, okay, because 0 is coming here. So, this plus this x minus m, this is coming here, this plus this x minus m plus 1, okay, 0 is coming here, 0 plus x0, x0, x1 is coming here, x1 plus 0, x1, like that, dot dot. So, say x0, x1 has come, then zeros, then xm, m plus 1 come, zeros, then you take the next one, okay, and shift, I mean expand by 2 and shift by 2. So, in that case x2 sample will come here, xm plus 2 will come here, like that. If you add, you get x0, x1, x2, and like that. So, this way the whole sequence will build up. So, in terms of Z transform, if it is P0n, capital the Z transform is capital P0Z, so it is P0Z to the power m, because expanded. It is P1 capital P1Z, so capital P1Z to the power m into Z inverse, so and so. P2 capital P2Z, then capital P2Z to the power m into Z inverse 2. So, overall Z transform will be a summation of this, that is the polyphase decomposition. Okay. H0 expanded, so H0 Z to the power n, then H1 expanded, sorry, this is H1, H1 expanded, and then Z inverse, because one shift. Next one will be H2 Z to the power m, because expanded, then 2 shift Z to the power minus 2 dot dot dot. This was your polyphase decomposition. So, Hz I go for this polyphase decomposition. So, xz into Hz means xz into this plus xz into this plus, like that. Okay. So, what you can do, this filter can be realized like this, x n, that is in terms of Z transform xz, xz into this component. Okay. Xz into this, then xz into H1 Z to the power m with a Z inverse. So, put a Z inverse, that into H1 Z to the power m. then another Z inverse, because next will be Z inverse 2 H 2. So, another Z inverse. So, total is 2 Z inverse, then again H 2 dot 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 dot. Lastly, and you have to add all of them because of this plus sign. So, x z into this coming here, x z into this coming here, x z into next coming here, all of them are to be added. So, you go on adding. Adder is always something which takes 2 input and 1 output, that is why we have to do so many additions. This is the output, and then you are decimating, right. Now, you see, if suppose two signals x n, suppose two signals h n, they are first added and decimated, first added then decimated by m, you will get the same thing. This is equivalent to first decimate this and then add. This is very simple. Suppose you have got x 0, then x 1 dot 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 x m here, then again dot 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 x 2 m here dot dot dot, and you have got h dot dot dot, let us say h again dot 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 h 2 m. Suppose you first add and then decimate, you will have x 0 plus this, then next m minus 1 samples you throw away, then take x m plus h m. Okay, so you will have x 0 plus h 0, then first sample will be x m plus h m, because you are throwing out the intermediate samples, then will be x 2 m plus h 2 m dot dot dot. So, if you add and then decimate by m, this is what you will get. On the other hand, if you decimate first and then add, you will get the same thing, because if you decimate first, you are throwing away this. So, this will become sample number 1, this will become sample number 2, this will become sample number 1, 2, 0, 0. Now, if you add x 0 plus h 0 present here, then sample number 1 will be x m plus h m present here. Then sample number 2 will be x 2 m plus h 2 m present here. So, either you add then throw away the intermediate samples, you get the same thing, or you first throw away the intermediate samples and add, you will get the same. Okay. If that be, then these two are getting added then decimated, I can bring the decimator here and here. Again these two getting added decimated. So, this decimator I can bring here and then here. Again these two are getting added then decimated. So, this decimator I can bring here and here, like that. So, I can bring eventually decimator will be here, 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 here. Okay. So, that means the new structure will be okay. This is a new structure, decimator has moved here, here, here by the process I showed. Now, we remember noble identity 1. What was noble identity 1? This was noble identity 1. If you have a x n processed by a filter of the form h z to the power m, that is already expanded by m zeros, m minus 1 zeros are there between every pair of samples. Originally h z, then between h 0 h 1 put m minus 1 samples, again m minus 1 samples, again then the resulting transfer function is called h z to the power m, it will be, we have seen, and then if you decimate by m, you will get the same thing if you bring the decimator first and then the filter where h z to the power m is replaced by h z. So, between h 0 and h 1 no zeros, this is 0th, this is first, between h 1 and h 2 no zeros, this is first, this is second, like that. So, this I can apply between these two, this decimator can come in the front, it will be h 0 z, then between these two decimator come in the front, it will become h 0 h 1 z dot 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 dot. So, this will be equivalent to this will be equivalent to it is now z because of the noble identity, noble by noble identity A. What will be this structure? What is the advantage of this structure? These filters are working at a lower clock rate, sampling rate, because sampling rate has first been brought down by m. So, now the clock is slower, m times slower, the filter is working at a slower rate. So, it is less costly. Whereas, previously first you had a filter which was working at the higher sampling rate and therefore, more costly, then you downsampled it. Okay. Only one thing you have to be cautious, sorry, there will be a Z inverse here. Only one thing, you cannot push this behind, because of the simple reason that if you have one sequence say, the delay and this cannot be interchanged. Suppose you have got a sequence x n, it is like this, this is your origin x 0, okay, then x 1 dot 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 x m, then again all these points x 2 m. If you decimate, if you delay it first, the Z inverse, if you delay it first and then decimate, if you delay it, x 0 will go here, x minus 1 will come here, x m minus 1 will come here, okay, this is the mth point. So, x and you have got all other data, I am not naming them. If you now decimate, what will you get is this guy, then this guy, then this guy, like that. So, you will have x minus 1, then x, this number 1 point, number 2 point will be this, x 2 m minus 1, like that, dot dot dot. That is, if you delay first and then decimate, you get this. But on the other hand, if you first decimate, if you first decimate it, you will get x 0, then number 1 point will be x m, then number 2 point will be x 2 m, dot dot dot. Okay. So, if you first decimate and then delay, now you delay here x minus m will come from the left side. At one position x 0 will come, 2 position x m will come, and we see this is not same as this is not same as this. Here at 0 x minus 1, here at 0 x minus m, here at number 1 x m minus 1, here is x 0. So, they are not same. Actually, this is not a linear, this is not a shift invariant. This is linear, but not a shift invariant structure, and that is why the two cannot be interchanged. The two can be interchanged, two systems, if both are linear and shift invariant, then overall transfer function is Hz, which is H1z into H2z, which you can also write as H2z into H1z. So, two can be interchanged, okay, but not otherwise. Capital, if you have got a system, H1z transfer function means system is linear and shift invariant. You have got another system in cascade, transfer function H2z, that is also linear and shift invariant. Overall transfer function is H1z into H2z, which is same as H2z into H1z. So, you can bring the block H2z in the front and H1z in the to the right, still thing will be same. So, they can be interchanged, but a decimator is not a shift invariant structure, you can verify, and that is why a decimator and a delay cannot be interchanged. But anyway, this is an efficient decimator structure we have seen, filters are working at a lower rate. Now, we go for the other version, that is expander. What do we do in the case of interpolation, rather not expander, interpolation. Efficient. What do we do in an interpolator? We first pass it through an expander, okay, and then you have a filter Hz, where transfer function is like this, ideally like this, pi by m minus pi by m, and then zeros up to pi and minus pi. These are transfer frequency response. Okay. You first expand by m and then pass it through this filter. If you have forgotten, go through my notes on interpolation. These are interpolator. We discussed this at length. Interpolator, first we expand between every two samples, put in m minus 1 zeros, so expanded, then pass it through a filter of this kind, ideal low pass filter if possible, from minus pi by m to pi by m, that is the pass band, and otherwise 0. If you pass it through this, output will be the interpolated thing. So, suppose this transfer function is Hz. Now, here you see first sequence was low rate sequence, some sampling clock was for that. Now, this is after expansion, it is becoming higher, faster sequence, because between every pair of samples I am bringing m minus 1 zeros. That is, I am creating between say x 0 and x 1, earlier so much was the sampling period, and so sampling rate was small. Now, I am bringing in intermediate sampling points, total m minus 1 zeros. So, now sampling period is tau, tau is, if total is t, tau is t by m. So, sampling period is going down, means sampling clock here is m times faster. So, the filter is working at a faster clock, m times faster clock means it is costly. How to bring down the cost, how to make it operate at a lower rate? Well, first you should see, I can still bring this, replace it by that form, that polyphase decomposition, as we did last time, and we will see it will not work now here. I am not drawing the remaining part, because I will not hold on to this. This will not work, we will see. We know the noble identity of that kind too. Just give me a minute. Yeah, noble identity of the type B. Here, if you first expand x n, so from low rate it becomes high rate, and then you pass it through a filter of the kind h z to the power m. So, here again in the transfer function between every pair of sample there are m minus 1 zeros, expanded version of impulse response. Then that is equivalent to first passing x n through h z where there are no such zeros between every pair of samples. So, filter is working at the same rate as the same sampling clock as the original input. So, it is less costly, and then you expand by m, you will get the same thing. So, if you apply that here, this interpolator, this expander, I can bring here, I can bring here. There is instead of here, there is first to expand between every pair of samples, you plug in zeros and then give here and here. Instead, you can do here. Also, you can do here. Same sequence, I am repeating the thing here and here. But again, these two cannot be interchanged. I cannot bring it here. Here, I see I can apply the noble identity B, that is into H 0 z to the power m and m. So, this will become this particular part will become H 0 z first, it will come here, followed by expander, this part will become like that. So, this will be working at a slower clock, but this interpolator expander cannot be pushed here. That is, if you have expander, this is actually that part I am redrawing, because it is little unclear here. So, this part is not equivalent to first delay and then expansion. That is, they cannot be interchanged. Very simply, why? Because suppose I have got a sequence is coming here, say x n. If I expand it, I will have x 0, then 0 0 dot 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 zeros, m minus 1, then x 1, which will be mth sample, then 0 0 0, then 2 ms sample will be x 2 dot dot dot. Then if I delay it by 1, I will have a 0 coming from here. So, 0 from the left, x 0 will move here, then these zeros at mth point also I will have 0, then at m plus 1th point I will have x 1, then again 0 0 0, at 2th point also 0, then at 2 m plus 1 I will have x 2 m plus 1 dot dot dot. On the other hand, here if I first delay and then expand, what will happen if I first delay this? So, original x n is first delayed. So, you will have x minus 1 coming at origin, then x 0 sample number 1, then x 2 sorry x 1 sample number 2 dot 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 dot, okay, because delayed. Now, if you expand, you will have 0 0 0, this will become mth, then 0 0 0, this will become 2 mth. So, you see 0th here is x minus 1, here 0th is 0, mth here is x 0, mth here is 0. Okay. So, the two are not same. That is because this is not a shift invariant structure, linear, but not shift invariant structure, that is the two cannot be interchanged. You can easily from here. If you first delay the input sequence and then decimate, delay means x 0 will move to position 1, x 1 will move to position 2, x minus 1 to 1 0, and then you are plugging in m minus 1 0. So, this become mth point, this become 2 mth point. On the other hand, if you first expand and decimate, the origin you have got 0, x 0 came to here, mth location till that point I have got 0 band, then have m plus 1th I have got x 1, then again a 0 band, 2 m plus 1th I have x 2 m plus 1, like that. So, these two are not same, you can see. That is why I cannot move it here to take advantage of the noble identity. So, this way I will not work, I could only do that here. Okay. This is m, and this will I could, that is I could interchange H 0 z to the power m, H 0 z comes first, and this expander that goes second. This can be interchanged here, because there is no delay. So, these two I can apply this noble identity B here, but I cannot bring that interpolator here and then apply noble identity B on these two, and same downwards also. So, this will not work, but I can get around this problem by a clever manipulation of this kind, that H z I know is Okay. You start with this first. There is top filter instead of H0 jet inverse this, let me write this. Then let there be one delay. Then next filter one delay dot 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 this is the situation. You see x n, there is x z into this, that signal passes through one delay z inverse. Then if you forget about these contributions, one z inverse, then again z inverse, total there will be z to the power minus m minus 1. Then next signal, okay. If you want, you can write the signal here, that is z to the power minus m minus 2. So, x z into this means x z into this part first, then that will go through m minus 2 delays. So, you forget about this top delay, it is going through one delay, another delay, total m minus 2 delays. Consider this x z into h 2 z to the power m, x z into h 2 z to the power m here, it should pass through two delays. So, one delay, another delay. Then consider this x z into h 1 z to the power m, x z into h 1 z to the power m, then that will pass through only one delay. Okay, and x z into h 0 z to the power m, no delay, and all of them get added in this process. Okay, this is called a transpose structure. Here, if I have this, I can happily copy it in every places, because expanded thing going here. So, same thing as, I mean, you can write like this, instead of having it here, that was originally. I can have the expander here, I can now have the expander here, I can now have the expander here. This is expanded, and then the expanded thing was going into all. So, I am making the expansion right at the beginning of the filter, that is at the input of the filter, same x n expanded going here, expanded same as before. Earlier it was expanded and going in, x n expanded going in, x n expanded going in, x n expanded going in. So, I am not making any change, but between these two, I can apply the noble identity B, and this will become this nice structure. Okay, this is the structure. And here you see the filters are all working at the same sampling clock at the input. So, and then only they are expanded, extra m minus 1 sampling points created and their zeros are put, that is the expansion meaning of expansion in all of them, and they are getting added. But before that, the filters, these polyphase filters, they are working at the lower clock, because that is there is a sampling clock involved with xn, present with xn, that is the original clock rate, okay, and that is lower. After expansion, that is higher. So, previously they were working after expansion. Okay, so, these filters were working at a faster clock. Now, they are working at a slower clock. So, that is why this is efficient. And by the same token, you cannot push this interpolator ahead of the delay, because as I told you, this expander ahead of the delay, because delay and expanders cannot be interchanged. Okay, because this is linear, but not shift invariant. You have seen it already. So, that is all for this class. We move to the next one. Thank you.